polynomial end behavior. We know a polynomial is a monomial term or multiple monomial terms held together through addition subtraction. So we might have some term ax to the n as a standalone monomial term, or we could start adding additional terms. So we could put a subscript here. We could say something like this, and this keeps going in theory till we get to some constant term. Now, because the polynomial is a sum or difference of monomial terms, or just perhaps a standalone monomial term, and the monomial term is defined with an exponent value that is non-negative integer, then we know there is no restriction on the domain. So our domain runs from negative infinity to infinity. We could, in theory, plug in whatever value we want into the variables and get an output. Now, we should make a note that our domain runs negative infinity to infinity, but we're ignoring applications. Say you have a polynomial that represents the volume of a box, and the variable represents one of the side lengths of that box. Well, then we would ignore any negative input values. So in a more pure sense of the term of the polynomial, the domain is negative infinity to infinity. And that's going to become important because when we're looking at the behavior at the ends of the graph, what we're analyzing is what is the function doing as x approaches positive and negative infinity. So this is what we mean by end behavior. We know that the polynomial will span the entire input axis, which is the x-axis, due to its domain. The question we're looking to answer is, where does the function outputs go as x approaches positive and negative infinity? So as we're going to the right and to the left forever when we're visually observing a coordinate plane. Now, the other thing to note is that the polynomials are continuous. They're nice, smooth curves with no breaks, holes, gaps. So where you don't have a formal definition for continuity at this point, but a really elementary definition is the function can be traced without picking up your pen or pencil. So knowing the continuity aspect, we know there's only a right end and a left end. So there's no ends in between. There's no breaks up. The graph isn't broken up into multiple pieces. And therefore, we don't have to observe end behavior upon multiple pieces, but rather, due to the fact that the polynomial is continuous in its entirety across the domain negative infinity to infinity, we only have to observe a right end and a left end, or in a more mathematical sense, as x approaches positive and negative infinity. So now let's just look at an example polynomial, and we'll see that to determine end behavior, we only have to really look at one piece of the function. So let's take a really simple example, like we have x cubed plus x squared plus x, say plus 1. So we have 4 monomial terms held together through addition. Now, knowing that the domain is any number I want in the real number set, as we start to input values, say we plug in 10, this would become 1,000, this would become 100, 10, and 1. So that's when I plug in 10. Let's say we plug in 100. If we plug in 100, we're going to have to 1,000,000 for the first thing, 1,000 here, 100 here, sorry, 10,000 here, 100 here, and 1. If we plug in 1,000, so you can see what's happening here is that this is as x approaches infinity. These numbers are getting larger and larger and larger. Now, as I approach 1,000, we're going to have a billion plus a million plus 1,000 plus 1. As x increases, you'll notice this constant term stays the same. This x term is only going up by a factor of 10. This term's going up by a factor of 100. And this term is going up by a factor of 1,000. So the gap, or the overall value of this polynomial, if we were to add these terms together, and you could imagine as x gets larger and larger and larger, in the grand scheme of things, 1,000 is a relatively small value considering it could keep going forever. You'll notice that the overall value, or where this thing's headed, is dictated by this first term. Okay, those are the numbers that are controlling where the overall value of this function heads towards. So when we look at a polynomial, the term of highest degree, or the leading term, is going to dictate where the function ends up going as x gets infinitely large in the positive or negative direction. Knowing that all we have to do, because as these keep getting larger and larger and larger, these become pretty much obsolete. Okay, the gap between the first term and the other terms is going to grow so large that all we really have to do is observe that leading term. Once you've identified the leading term, there are going to be 4 possibilities to determine where the ends of the graph go. So you can see overall, as x went to infinity, this graph, the values just kept getting larger and larger and larger in the infinite direction. So there's 4 scenarios. If we have our leading term of the form ax to the n, the leading term is going to be our term of highest degree. So we've been able to identify degree of monomial terms. Once we have done that, there are only 2 things we need to look at: the degree itself and the leading coefficient. We could have a is positive and our degree is even. We could have a being negative and the degree is even, a being positive and the degree is odd, or a is negative and the degree is odd. So let's observe each of these scenarios and determine what the end behavior should be. So for the first one, positive even scenario. We know our function spans the entire input axis and therefore extends to positive and negative infinity, and we are interested in where does the function head towards when that occurs. So in the event that we have an even exponent, imagine taking some value that continually gets larger and raise it to some even power. Choose whatever you want, 2, 4, 6, whatever. Okay? In the positive direction, if I raise it to an even value exponent, that number will just continue to get larger in the positive direction. So it's still heading towards positive infinity. And if I multiply it by a number, that leading coefficient that's positive, it only grows in value in the positive direction. So the function should head towards positive infinity. Now visually, what does that look like? On the coordinate plane, as we head towards positive infinity, so positive infinity is this direction, negative infinity. So as we're moving this way, the function graph at some point will start to head up towards positive infinity. Now, as we head towards negative infinity, imagine taking a value that's negative, growing in the negative direction, and you raise it to an even exponent. If you take an even value, a negative value and raise it to an even exponent, say 6, you know that it's going to turn positive, but it's still growing in an absolute value sense. So the magnitude of the number continues to get larger, but it will become positive. So taking that negative value that's growing in size, raising it to an even exponent makes it positive, and then multiplying it by a positive leading coefficient keeps it positive. So the overall value grows in magnitude, but becomes positive. And therefore, as you head in the negative direction on our coordinate plane, the polynomial function values should at some point head towards positive infinity. So the end behavior for this first scenario would be written in that way. As x heads towards infinity, the function should go towards positive infinity. As x approaches negative infinity, the function approaches infinity. And visually, both ends of the graph at some point should head up. And it's worth mentioning that this end behavior is strictly telling you what's going on at the ends of the graph. So this will not provide us with the information needed to determine what's going on in between, because we know, as we said at the beginning of the video, the polynomial is continuous. So it should be connected with a smooth curve in between. But what's going on in between, we need more pieces of information, and that's for another time. So strictly looking at the ends of the graph, but just know, keep in the back of your mind that the function is continuous and there is something happening in between those ends. So let's go to our next scenario. Well, knowing that the positive leading coefficient even degree scenario, both ends go up. If I change the leading coefficient to a negative number, so imagine if we had some term x to the fourth, that is a positive even leading term. And if I make the leading coefficient negative, then we discussed at the beginning of the year with transformations, multiplying by the -1 will be a vertical reflection. So what I would expect is that instead of both arrows going up or both ends going towards positive infinity, they should now be going towards negative infinity. And we can support that through some analysis. So we know that the graph will head towards positive and negative infinity because of its domain. So imagine plugging in a value that goes towards infinity in the positive direction, raising it to an even exponent. We've already discussed that that should get larger in the positive direction. But if I multiply it by a negative number, the overall value will go towards negative infinity now. So it's going to just change the sign. Now, if we go to negative infinity, raise it to an even exponent, it becomes a positive number, growing in magnitude, but then multiplying it by a negative number changes it back to a negative value. So both ends go towards negative infinity. So in the negative even scenario, as we go in either direction, left or right forever, both ends of the graph at some point should be heading towards negative infinity. So visually, some people like to put the arrows as a reminder. Third scenario, the positive odd case. So if we have an odd exponent and a leading coefficient that is positive, imagine taking some value that's headed towards positive infinity and raising it to an odd exponent, say 5. This will grow in size in the positive direction. So it'll still go towards positive infinity. And multiplying it by a positive leading coefficient keeps it growing in the positive direction. So it's going to head towards positive infinity. If we evaluate a negative value growing in magnitude and raise it to an odd exponent, raising a negative number to an odd exponent keeps it negative, and it will be growing in magnitude just in the negative direction. Multiplying it by a positive leading coefficient keeps it negative, so that will go towards negative infinity. So you can see here that the ends of the graph will go in opposite directions. As we approach positive infinity, at some point the graph should start heading towards positive infinity. As we go towards negative infinity, at some point the graph will head towards negative infinity. So that is your positive odd scenario where the right end goes up and the left end goes down. And then the last scenario is the negative leading coefficient odd degree case. We expect that we know the positive odd case, and if I change my leading coefficient to negative, envision a vertical reflection occurring. So we expect the direction of the ends to just be reflected. So the left end to go up, the right end to go down as we head in those directions. Through some analysis, that should be supported. If we take a positive value, raise it to an odd exponent that's growing in size, it still remains positive infinity, but multiply it by a negative value, it changes signs, right? Then if we take a negative value, raise it to an odd exponent, it remains negative, growing in size, so it's going in the negative infinity direction, but if we multiply that value that's growing in magnitude in the negative direction by a negative number, it becomes positive. So you can see here that as we approach infinity, f of x goes to negative infinity, or down. And as we approach negative infinity, it goes to positive infinity, or up. So left end goes up, right end goes down. So in conclusion, the four cases, you'll notice that the even degree scenarios, the ends of the graphs go in the same direction. The odd scenarios, the ends of the graph go in opposite direction. And to determine end behavior, all it takes is analysis of the leading term, or the term of highest degree. Because as the values grow in magnitude, as x goes towards positive and negative infinity, the other terms in the polynomial do no longer matter. As the numbers grow in such large sizes, that leading term, the term of highest degree, is going to dictate the path of the polynomial overall. So that's all you have to look at, and that is how you determine end behavior for the polynomial. Only four scenarios. If you know the two positive cases, or you can analyze or derive the two positive cases, then you know the two negative cases through the idea of reflections.